We're about to dive into a story that starts with a number you've probably heard of, but it's going to take us to a place that you would never, ever expect. It's a mathematical mystery that reveals this beautiful, hidden order in the universe of numbers. And it all kicks off with a number that has totally fascinated people for centuries. We're talking everyone from ancient Greek architects designing the Parthenon to biologists looking at the spirals in a seashell. So you've probably heard of it, right? The golden ratio. We call it phi, and it comes from this surprisingly simple little equation you see here. Z squared equals 1 plus z. It's the one and only positive solution. Okay, but here's where the real fun begins. What if that famous equation is just the tip of the iceberg? What happens if we start messing with those powers? What if that 2 and 1 are just the start of something way bigger? Well, that one simple tweak, bam, it opens up this entire infinite family of equations. Our golden ratio is just the very first member, the case where n equals 1. But now we can see what happens when n is 2 or 3 or 100 or literally any whole number you can think of, all the way to infinity. So now that we have this infinite collection of equations, a brand new question pops up. What are all the solutions? Let's go on a hunt for these solutions. We call them roots, and see what kind of patterns we can find. A really cool way to picture this is to just graph both sides of the equation. The real roots are simply the spots where these two curves cross each other. And as we change n, the shapes of these curves change, and so do the points where they meet. And what's just incredible is that out of all this potential complexity, something super simple appears. For every single value of n, it doesn't matter how big it gets, there's always exactly one positive real root. Just one. For n equals 1, we get the golden ratio, right? About 1.618. Well, as you crank up n, this positive root just gets bigger and bigger and bigger, marching steadily off toward infinity. But that only accounts for one root. What's happening on the negative side of the number line? Well, here things get a little weird. When n is an odd number, we find exactly one negative root. But when n is an even number, that negative root just vanishes. Poof, it's gone. It's like this mathematical game of now you see it, now you don't. But the real number line, that's just one dimension. To get the full picture, we have to go bigger. We have to enter the complex plane. And it's here, in this two-dimensional world, that all the other roots show up. They always appear in these perfect, balanced pairs, and they finally complete the puzzle for each equation. So this brings us to the big, big question. If we could somehow plot every single root from this entire infinite family of equations, what would we even see? Would it just be a random mess of dots all over the place? Or is there some kind of hidden structure, a secret order holding it all together? The answer is just so simple and so beautiful, it's almost hard to believe. As n gets bigger and bigger, all those complex roots, all those flickering negative roots, they don't scatter into chaos. They are all drawn towards a single, perfect, vertical line. You can almost think of this line as having its own kind of mathematical gravity. As n gets bigger, the constellations of roots from each new equation get pulled closer and closer to it, arranging themselves in this precise, elegant formation. It's just a breathtaking example of order emerging from what seemed like it could be total chaos. Okay, so this is a really elegant, beautiful pattern. But so what? Is this just a neat mathematical curiosity, or does any of this actually matter in the real world? Oh, it absolutely does. In the real world of physics and engineering, a lot of systems are described by something called characteristic equations. And guess what? They often look a whole lot like the family we've just been playing with. And the roots of those equations, they are the key to everything. Basically, where these roots land on the map tells you everything about whether a system is stable. If the roots are in one area, the system is steady. But if they cross a boundary into another region, that system might start to oscillate or even spiral completely out of control. Our beautiful line of convergence often acts as a critical boundary in these real-world problems. And to think, all of this came from just a tiny tweak to an equation we thought we knew so well. It really makes you wonder, right? What other incredible, beautiful, hidden worlds are just waiting for us, concealed inside the everyday math we think we already understand?